Okay, good morning, everybody, or whenever you are seeing this lecture. Again, we had a journey now through the different data that can be acquired in system, and we had mixed in already a few linear approaches of machine learning. We are in the beginning of this lecture series, so we are trying to get the language right that we're doing so that we can communicate the more complex stuff. So we started with imaging. Oh, okay, to do something. Okay, I have to see me what I don't know what I'm doing, which can be a problem. So we did all the electron microscopy, except one very important method, and that is diffraction. So we talked about imaging, we talked about EELs, we talked about how accurate we can get that. There are two things missing still. One is diffraction by itself. So when you are in STEM mode, for the ones who haven't done that before, if you're in STEM mode, you are in a diffraction mode. So you scan your probe, and what you do is you use different parts of a convergent beam electron diffraction pattern, like the one we have here in the background. So you use different parts of that for imaging or for analysis or what. So the key is to understand diffraction. And if you want to understand convergent beam electron diffraction, you have to understand that there are two relevant different modes for STEM. But so we have to go back to diffraction and see what are the difference to other diffraction methods, let's say X-ray diffraction, neutron diffraction, because we might want to combine them as well, right? So we go out of our PDF that is online, and we go here to lecture 8, and we use our first notebook. That is kinematic scattering. We open that in Colab. And we download all packages that we need. Most important, PyTemlib. So PyTemlib is a microscopy package that gives you most of the data analysis techniques. And what we are going to do with them, of course, is we want to produce data that we can then train machine learning algorithms on, right? So your neural networks, whatever. So that's why we are going over that. So we have one more lectures on data that will be about image simulation. Again, if you can simulate your images, you have your training data. So that is one part of this objective here. The other one, of course, is to understand what's going on. So while we are loading these packages, so I ran now the first two code cells. We talk about diffraction, and if we talk about diffraction, we actually talk first about Bragg's law. As a reminder, people who are not always doing that might not know. So we are talking about an electron beam. Now it comes in this. Oh, okay, it's not scheduled. Okay, so we come in and we have a series of atomic planes, and the path difference between two of these beams should be a multiple of the wavelengths, and in that case you have constructive interference. If you have destructive interference, you don't see anything, and this is pure trigonometry. Okay, this is going to be a trigonometry class. As one friend of mine said, if you do trigonometry, do it not in public. It's not a public viewing sport. Okay, you have to sit down and do it by yourself if you want to get to somewhere. So this is the real space, and in real space, we talk about scattering. If we talk about waves, we call it diffraction. And in reciprocal space, we have a reciprocal lattice vector that is related to the distance of these planes we are scattering on, or in our case now diffract, right? And it is 1 over the real space, so it's reciprocal space. The incoming and diffracted beam is given in the same way, so same angle, right? Coming in, coming out. And now we are, however, having vectors. This vector we can move. So we move the starting point of this vector up here, and we get a nice triangle. These two sides have to be always the same. So we do kinematic scattering. That means our electrons don't lose any energy. That means the wavelengths of these particles are always the same, so the de Broglie wavelengths. So we have a nice triangle, but since we know that these two vectors have the same magnitude, we know that all we have to do is put a circle around it, and then we have all the possible wave vectors from the incoming one. And this is the Evald sphere construction. So this is very, very basic, right? Physics 101. Just a reminder. How do we use that now to make data and to analyze our data? And actually, this is exactly what we were doing when we were looking at the diffractograms and put our Bragg spots on it. Then we know where the Bragg spot is supposed to be, where they are. We were scaling our image accordingly. So this is basic, but we are using it. And what we have to do is trigonometry. So it's fast to determine to create these data sets, and that's what I want to show you. So first we define a crystal. All the crystallography we need in this lecture is that, and we use the atomic simulation environment, ASE. It's a Python library. It has all the crystallographic functions that we need, and we will use that also for our image simulations, and you can even do MD simulations, ab initio calculations, all based on that. So it's really powerful, and so that's what we are using for our structures in picroscopy. We're really grateful to these people, so they did an excellent job. So as usual in Python, you're not trying to recreate things, you try to create combine stuff so that you get new and interesting things. So we need a crystal, and the crystal is, for our purposes, a unit cell that is periodic or translated in all different directions and fills the space completely. So that is one of the key things of a unit cell. It has to fill the space completely. And then within this cell, we have the basis of the atoms. And that is all the crystallography we need. Okay, a unit cell, and where are the atoms in this unit cell? In our case now, we have a cube. That is our unit cell, cubes all directions, and we have 8 atoms within this cube. That's called silicon or diamond structure. We need the length of our incoming wave vector. That is the wavelengths, right? Or 1 over the wavelengths. The wavelengths is in the order of a few picometer, and 1 over the wavelengths gives you the wavelengths magnitude. So we give that out here. Formula can. So it's a relativistic wavelength. So this is relatively straightforward. So now we have to have this real space crystal in reciprocal space. And that is something we learned all in physics. You learned it too, might have forgotten it. The way we do that is we using the ASE. Can we make this bigger? Oh, yeah. The ASE atoms object, we just say, get me the reciprocal, and they take care of all the intricacies that might happen, but really it's just going in reciprocal space here. And what we got is a unit cell in 1 over the unit cell, okay? And the question I always ask my students when I do that the first time, and they always say, yeah, we know all that. I ask them, where are the atoms in the reciprocal space? And I'm not going to answer that. It's something for you to think about. And maybe we can talk about it later. It will come up, I guess. So this is a single one. What we need is lots of them, and we need lots of them in 3D. So reciprocal space is a 3-dimensional space. We look at diffraction patterns. So what we often forget, it is just a projection, okay? So we have many of them. And what we do is we see how many Miller indices, so are we going to have? So what is the maximum reciprocal space that we're using? And so that's going to be done in Miller indices. So that is all the different spots in there. So we just multiply that. And now we have to come to a few definitions that we're going to need. So this is how we normally do a projection in reciprocal space. So we don't need really a lot of atoms in the direction of the electron beam, but we need a lot of them in the plane. But it's in all 3 directions, okay? We'll visualize it in a moment. And we define 1 point as the origin and 1 plane here, the plane perpendicular to the incoming beam, that is the 0 or the Laue zone. And usually you don't care about it in other diffraction techniques, but of course it's 3-dimensional, so there are other Laue zones as well. There's the 1st order Laue zone, 2nd order Laue zone, 3rd order Laue zone. But what we usually say is we have the 0 order Laue zone, salts, that is what you're used to from diffraction, and then the higher order Laue zones. Okay, how does that fit now with our diffraction part, right? So now let's see what the Evald sphere looks like in that thing. This, I think I made, let's see what kind of, I think that is only 30 kV or so. So it's a relative low voltage. And this is my reciprocal space from before. This is my starting point. So this is the reciprocal lattice vector, 1 over few picometer. Okay, so it's huge. I'm not sure whether you can see that, but if we zoom in here a little bit, oh, that's good. This is the Evald sphere cutting through the reciprocal space in the relevant area or volume. So that's the blue one. This is what you have in X-ray. You see the difference. And now let's see what happens if you come in here. The Evald sphere of our electrons are basically flat. We have a very high curvature in the X-rays. And so in X-rays, if you come in straight in zone axis, you will not have this reciprocal lattice vector activated. So you're not scattering in that direction because it will be too small. So the theta to theta scans that we do in X-ray diffraction is basically rolling around this Evald sphere so that we are hitting the different reciprocal lattice vectors precisely. It has its advantages, but the electron diffraction has the advantage that we are using this flat one, and so we have all of these diffraction patterns at the same time. So that is the difference. So we need to hit that directly, and or more or less directly. And so if we want to hit it directly, we have two options. And you can see that if you tilt the sample, as we do in a theta to theta scan, or if we tilt the electron beam and the X-ray thing and leaves these crystals the same, we hit always at the same place of the crystal with the Evald sphere. So tilting the beam, tilting the sample is the same. And if you're on a microscope, tilting is like moving in reciprocal space, right? So that's the options that you have. Okay. Let's talk about the precise Bragg condition for the tilted sample and the tilted Evald sphere. So now the K0. K0, here it is perpendicular down, right? Now it is with some angle. And we hit, oh, I should change my color here. We hit our reciprocal lattice point here exactly. That is the exact Bragg condition, and it is used extensively in conventional electron microscopy. Not part of this, obviously, but there are some imaging conditions where you want to look at in STEM mode as well, in two-beam condition, and that would be the way you do that. Okay, so we have this exact Bragg condition, and it is relatively rare, or you have to really work on that. But if you look at the diffraction pattern, get rid of that. You look at a diffraction pattern, and now we have 100 kV, just to have it not too. We will have a Bragg peak, even so that we are a little bit off with our Bragg condition. And the difference between the exact Bragg condition or the vector between the reciprocal lattice point, which are our Bragg conditions, and the Evald sphere, that is what we call the excitation error. So this is a very important vector, and without that, you cannot understand 4D STEM, which means you cannot understand STEM. So part of this lecture is really to get you to understand what this excitation error is. If it points up, the excitation error is negative. That is a convention. If it points down, it's positive. So if it's planned, if it goes in the same orientation as your incoming reciprocal wave vector, then it is positive. If it points against it, it's negative, right? And you can see we have a right angle here. And so again, everything here is trigonometry. Okay. So where does this excitation error come from? The key thing is that this reciprocal lattice vector, or reciprocal lattice point, not vector, so in this case we talk about the point, is a point only in the ideal case of having an infinite crystal in all 3 dimensions. As soon as you have a shape to it, like a disk, our samples are usually relatively flat but wide in X and Y direction, then you will have this shape, the reciprocal shape of that, which would be then a long tube, so-called railroad, convoluted with this point. And it gets even worse. So we put everything that is not kinematic into this excitation error. Okay. The dynamic diffraction, so it means double diffraction, so the shifting backwards and forward of intensity, the shape, everything is going to be in what this spot here exactly looks like in 3 dimensions. And it will be a relatively complicated figure. And why I'm saying that? Because your diffraction pattern in STEM, so the convergent beam electron diffraction pattern, is basically a map of this excitation error. So we're gonna have to understand the importance of that just to do that. And so if we zoom out, we see that we have this very small deviation here, and we call that the excitation error. We have our Bragg reciprocal lattice vector to this point, plus an excitation error to the Evald sphere. And the Evald sphere is given a refracted one that is not exactly hitting that. Okay, so that is our excitation error. And again, it's a shape. Now, if you have nanoparticles and you think it's a disk, this will surprise you, right? So we have to know what we are doing, what kind of shape we have. There's a lot of information in there. This excitation error makes electron diffraction or convergent beam electron diffraction the most precise diffraction techniques that there is. So again, part of it is the sample shape. And I made a 3D notebook at some point, so it's in my GitHub repository of my lecture. So the center of the Evald sphere is from the origin of our reciprocal lattice straight up or under some angle, but the distance is clear. It is the center of the Evald sphere. with a small correction. What is the small correction? Now, the electron sees all the nuclei shielded by the inner and outer shell electrons that these atoms have, but the potential it sees is actually positive. That means our electrons get accelerated within the samples. Okay. We already at 3/4 of the speed of light. The speed of light might be smaller in the crystal. That leads to Cherenkov radiation, so retardation effects. We haven't talked about that in Laue's eels, but that is one of the things that are usually considered a nuisance. But if you go back to the physics of it, you can actually use it for your analysis. So again, a different effect. And at the time, I didn't use it. So what we have now is our excitation error, and because the angles are so small, we can get rid of the trigonometry part, tangents, and go back to a linear equation that we can determine that. So we can now determine the excitation error for all of the different reflections. And we can then sort it out how many of them are close to our Evald sphere. So we have, in our case, a few thousand reciprocal lattice points. And so we have 361 that have an excitation error less than whatever we give it. And that is 1/nanometer. And in principle, you can make an estimate for 1 your sample thickness, right? So it's a rough estimate for that. Okay, so now we also have to put something in that is called the structure factor. That is whether we interfere at this lattice point constructively or destructively, plus our internal potential. And so we are going to have this, not talking about structure factors here, would get us not really somewhere, but you can just calculate them. Again, it is a formula that you can easily find. We add the inner potential to our internal lattice vector, and then we need, for a diffraction pattern, a zone axis, a maximum HKL that we want to explore. We use it as big as we want to. So we are doing trigonometry super fast, right? And we do an excitation error. So that are the ingredients that you need. And if you go back to the notebooks that we used when we did the Fourier analysis of the images, you see we used very, very small HKL max because we didn't want to go out far, and our excitation error was small as well. So only very, very bright peaks are there. Acceleration voltage consistent to our electron microscope. And then what we do is we calculate the possible reflection, and from them, how many of them are allowed. So we have about 400 allowed of this 400,000, about 400,000 that we checked. We have about 400 that are allowed, 57 in salts, and about 350 in the higher order Laue zone. Ooh, okay, so we have a lot of them. And the higher order Laue zones are the ones with the very, very high angles. And that is what we use in C contrast imaging. And that's what gives you a background. So it's not that you can forget any of that. Okay, so we really need to know more about it. Let's plot that to visualize it. We have an Evald sphere, and now we look at all the atoms that are allowed. So they are close to the Evald sphere within a small excitation error, positive or negative. And okay, let's see how good it works here. It was animated out here. Let's zoom in a little bit. Okay, so we see on the Evald sphere we have the zero order Laue zone, and then as we go out in the reciprocal space, we also get the other one. I say out, so let's tilt that thing. Oui. Okay. Let's go back. Okay, you can imagine this is your diffraction pattern. So what we have to do is now we have to project that down, but we can see the inner parts, the zero order Laue zone, it's the inner angles. This one or the higher angles. So the inner angle is your bright field image, dark field image, and these ones are the background in the higher order in this C contrast image. If we get rid of the Evald sphere, then that is what we get. Now we tilt the thing. You try that. You can do it, but I cannot do it while I'm on screen here and standing. So what we do is we get the rotation. Wherever we come in the zone axis, we tilt up. We have two angles, right? And in X and Y, and we just get a rotation matrix depending on the zone axis that we're using. And then we rotate everything else with the same one. And of course, in NumPy, it's trivial to do that. And then we plot that in 3D. So this was our Evald sphere that we now oriented our incoming beam in the 0, 0, parallel to the z-axis, right? And project it down. We make a small error here. So what I do is I just project it down. So I just get rid of the C component. What you really would have to do is, where does this deflected beam hit a plane? So that's what we really do. But these angles are so small in an electron microscope, you can ignore that, and that saves you a very time-consuming projection step. Okay, so we have defined excitation error, and we now know what I'm doing in order to get in the images my diffraction pattern. Or if you have a diffraction pattern and you want to simulate that, that's what you do. And the machinery is based on trigonometry only. Okay, so in STEM, now we want to go from our parallel elimination that I assumed here to a convergent beam one. And that's what I wanted to do here in the PDF. So we have now gone over the background of the vocabularies that we need to understand what I want to say here. Okay, so that's why I thought I need that to remind you, or if you haven't done much diffraction, this excitation error is a new concept for you. So here we do incoherent diffractions. That means the electron beams do not interact to form an image. So it means that the different Bragg peaks do not overlap. Okay, so there is an interference term in the Bragg law, but after that, the peaks are independent. They are connected with the dynamic diffraction, so they exchange intensity, but they don't interfere once they are scattered. Okay. We talk about coherence in my next lecture. It's the last lecture I give in this lecture series. So it's going to be on the 7th of July. So there's one lecture in between. And relevant for 4D STEM, it is if you do anything that is called nanodiffraction. So scanning nanodiffraction, that is all the information you get from that. So what can you get? Strain field around it, dislocation, interface, anything like that. Often nanoparticles, the exact lattice parameter, inside, outside, whatever, right? So spatial resolved lattice parameter. And the question is, how good can you get that and how should you set it up? So that's what we do. Why would you do convergent beam electron diffraction? Of course, you'd want to do 4D STEM. So you are in CBET mode anyway. That's one way to look at it. But you have some advantages. So you see Kikuchi lines. They're much easier to see in convergent beam electron diffraction. You have still the same advantages that you have with spot pattern, with parallel illumination. There's no difference. Your probe volume is very small. Okay. Can be smaller than a nanometer squared, so you get sub-nanometer resolution. You get more symmetry information, and you get this higher order Laue zone diffraction information into your diffraction. And that is giving you a third dimension, right? So let's go back to our thing here. The distance from here to here in along. Do I still have? No, I messed that one up, right? Okay. So here. And oh, you see, I didn't tilt really very well. Okay, good enough. So from this plane to that plane, this is the third dimension of your unit cell. And so it means we have now information about the third cell. And that means you can get the full strain tensor out of a single diffraction pattern. So that's the idea behind it. Let's go back to our thing here. So that's why we do convergent beam diffraction. You get 3D information, you get very precise diffraction information, and you get a lot of information, but it's very, very local. You can scan it, then you get a map of it. If you want to use, however, you should use it symbiotically to normal diffraction. So just to check what's in there, what kind of phases, getting selected area electron diffraction. So in parallel illumination, your diffraction pattern, ring pattern is extremely fast and easy. So it will be not very smart not to do it, right? So let's talk about this new feature I was talking about, this Kikuchi lines. So the Kikuchi lines are all the lines that you also see in EBSD and that you use for orientation dependent imaging. What is it? How can we understand it? One thing to begin with, you can not get rid of it. So you come in and here is your sample. our normal Bragg reflection. And we're not talking about that at all right now, okay? So forget any of these Bragg spots. We have also scattering on inelastic scattering on phonons, other inelastic things, and they go in all directions. In the very first orders, they go in all 3 dimensions in the same direction. So they have slight forward directionality, but we forget about that. That's for a Gedanken experiment, say they all go in all directions homogeneously now. So part of these electrons move anywhere they want to. And what you would get is, of course, an homogeneous gray background. But some of these electrons that are scattered all over the place are now in a Bragg condition with some kind of lattice planes. And so instead of going in this direction here to the right cone, they go to the left cone. For me now. Anyway, so we have, instead of going in this direction, they go in that direction. And that means we have a deficient line and an excess line. Okay. The beauty of it is like a diffraction pattern where the origin is inside your sample. That means they are fixed to your sample and nothing can change that. And so we are using that to orient ourselves in reciprocal space. And so they're extremely useful. They're always in your 4D stem image, 4D stem diffraction pattern. So it hits your detector in one way or the other. So we have those. And we also want to understand the higher order Laue zones, which are actually Kikuchi lines for the Holtz lines. So we want to understand those, and they have the same kind of origin. So instead of going straight through, we have these Kikuchi lines. And it goes also backwards, right? So that's why you have it in SEM. The next thing that we have to do is we have to look into convergent beam electron diffraction. So if we have only one angle that we come into the sample, then we get a spot pattern. If we come in straight, then we have one in the middle, and all the middles are from one spot, right? If we come in with a different angle, then this different angle also will make a spot pattern. But if you tilt your sample, or if you tilt the beam, and so now we have several tilts here up before we do the sample, and that is your convergent beam. We do that is equivalent to changing the sample, tilting the sample. If you tilt the sample or tilt the beam, what you get is different excitation errors. So each point here has a different excitation error. Okay. Let's assume, for the sake of the argument, we are putting excitation error 0 here and here. Then all of these maps have different excitation error. So we look at the map of excitation error, which is a convolution of sample shape and dynamic diffraction. And that is where the power comes in. Okay. The convergence angle is just the size of your disk, so it's very easy to measure, right? And you can measure the Bragg condition, Bragg angle, by just going from one center to the other or from one side to the other. So that's still preserved because the disk size is always the same. So that's trivial, right? You have fundamentally three different ways of doing it. This is basically a spot pattern. So that's not relevant for STEM. So you're not getting there. So you don't want to do that. That we wouldn't consider that STEM anymore. If you have very, very small angles. We can do it, but we usually don't. And the reason is, if you go to a little bit larger angles where the disks just change, where the disks just touch each other, then you get your nice map of excitation errors. So on top of just where the Bragg spots are, you get now excitation error information. That means you have a structure in the spots, and we'll see how that becomes important. Also, you see your Holtz rings better, and that means if you have here an excess line, you will have deficient line here, and that is what we were going to look for in the Holtz line detection. And if you have the overlapping disks, then you have coherence effect. So after they overlap, it brings them to coherence, and that is what we normally use in scanning transmission electron microscope. So this is in the order of less than 1 milliradians. This is about around 5 milliradians or so convergence angle. And this one is what we normally use. It's about 30 milliradians, depending on the coherence of your probe, 30, 40. But again, you see, we have these Kikuchi lines, and we have these overlapping ones, and we cover that in my next lecture that I will do in Friday in a week. We do a simulation of that. If I'm in perfect two-beam condition, now I can actually look at that, and I can look at the excitation errors of that. It's a very powerful method, and you actually can get the charge density of your sample from this kind of things. As I said, it is very powerful. And so S0 is here, and then you go in the different directions here, and you have different excitation errors as you go along. Why do you see the higher order Laue sound so much better? Instead of having just one Evald sphere, now we have two limiting Evald spheres. And in the higher order Laue zone, you will hit the one or the other higher order Laue zone Bragg's peak perfectly. And so that gives you a very good signal. So there, generally speaking, excitation error 0 will give you very strong Bragg reflection, right? So that's what we want. So we get our higher order Laue rings, which are directly related to the C height. So the one parallel to the zone axis that we come in, and you get those informations. So we use the different excitations, deviations in our Evald sphere of our convergence angle, our converged beam deviations, right? And we have excitation error. As I said, going down is positive, going up is negative. And so in our disks, we have now excitation errors, positive and negative. And so the whole disk is the same Bragg condition with different excitation errors. And as you go along, you have different excitation errors depending on what your exact tilt is. And again, this is the one for the exact two-beam conditions. If we go in two-beam condition, we do it very accurately. Now here's my cartoon of where you have positive and negative excitation errors. And you can think about it with the Evald sphere. And then now if we look at this kind of convergent beam electron diffraction pattern, we know this pattern are our excitation errors. We can simulate those. And we can use the patterns directly because they give us an information about symmetry. And we have a symmetry of the zero disk and the outer ones. Now, funny enough, the zero disk has the deficient lines of the higher order Laue zones. So that gives us a 3D information, and this one gives us the 2D information. And then we can combine these two to get somewhere. Let's look at that. And we can actually also get the thickness out of that when we do the dynamic diffraction that we have to go over a little bit. Then you see that the thickness fringes, so when the zero beam, depending on the excitation error, gets intensity out to the other diffractions, and it's dark. So we have thickness fringes here. So you actually know the thickness and the exact symmetry of the sample by just analyzing this data set. Generally speaking, this is what you can get for each single. Work. And then we get a plot where we plot the 1 over the thickness with some order, excitation error, and this part here with the extinction distance. The extinction distance is directly related to the inner potential of your material. So if you're interested in that, look it up. And then there's a recipe for that, relatively straightforward. And so what you get is diffraction pattern in two-beam condition. So excitation error 0 in the center. And then you look at the profile here, which is this, and you measure how far apart those are with respect to the convergence angle. So it gives you an excitation error. And then you plot that, and wherever the slope gives you the extinction distance, so that's your inner potential related term. And where it is here, it gives you the perfect thickness of your sample. And that is accurate to sub-nanometer. So very accurate, but only for the crystalline part. If we want to use all higher order Laue zones as a ring, so we get the third dimension of our lattice parameter, not only x, y, right? We talked about that. And so we record the Holtz and the Zoltz pattern, both of them. That is normally not done in 4D STEM, but it's very useful. Then, because it is related directly through trigonometry, we can correlate that with the wavelengths and the radius of this higher order Laue zone, and you get actually these rings. Can of course also simulate them. It's automatic, right? So we did that already. And then for FCC, we have also different selection rules. So that is your structure factor 0, which means it's a forbidden reflection, it will not show up. Or is it allowed? Then it is positive. So we have different excitation errors for that. And so selection rules for that. And so we can look at that, and they're known for the different crystallographic crystals. So you get from the Holtz rings already with the selection rules a good understanding of what's going on. If you don't know it, is it the first ring? Is it the second ring? Well, we can actually determine that directly by overlaying the zero-order Laue zone pattern with the higher-order Laue zone pattern and see how they combine. In a primitive one, it will just coincide. In So here's a coincide in an A-centered, B-centered, or I-centered. So it's a BCC. You see how they coincide in some direction or the other. So you can look at that, and by just extending that, you can see whether it's FCC, BCC, and so on. If you're interested, there is a notebook in the diffraction part of the MSE 672 Introduction to Material Science in my notebook. Key thing is we get this three-dimensional symmetry from our sample locally. And symmetry, again, it's something you have to work through yourself. One of the key things, however, is that you have 32 point groups that are different in their symmetry. In normal diffraction, you can separate out 11, the so-called Laue groups. The key of we have the diffraction groups in convergent beam electron diffraction. And the reason for that is we have our excitation error pattern. And that means that our spots now are not just spots, but they have a structure. So while the mirror symmetries might be giving you two-fold and four-fold mirror symmetries or three-fold, they would be all the same for you. Now that you have structure in your spots, that doesn't look like that anymore. So this one would be six-fold, but because this one is green and this one is red triangle, red star, so you cannot fold this one on top of that. And this is not longer a mirror symmetry, the red one. So you have suddenly threefold symmetry, threefold symmetry, but no mirror planes. So except here, you have one mirror plane, sorry. I just see that. Anyway, and the same thing is if you have a single spot, so it would be the center spot, that has a symmetry. So you look at the symmetry of the whole pattern with their excitation error and of the zero spot. On that, you can get actually the full point group information with some tabulation and so on. Okay. So we break Friedel's law because of the dynamic conditions that we have. So that is in our thing, and then we can look for the symmetries in these different parts. So if it is possible, not only takes the zero, this takes the other ones as well, and you'll be able to determine small deviations, changing in the breaking in the symmetry, and so on. It's all possible. You can look at polarity in polar materials, all of these things, and you can do that locally in a scan. Okay, talked all about that already. So let's go and look how accurate that stuff is. And we do that with our notebooks. Okay, more or less on time, a bit behind. So we go and start the next notebook. It's under lecture 8, the Kikuchi lines. And I guess we have to go through that one a little bit faster so that we can talk about Holz lines a little bit more. Kikuchi lines. Let's start with loading them. So we need the PyTemlib because I have also kinematic scattering in here. There's also some dynamic scattering, gets us the wavelengths, all of that stuff. Oh, good morning. Cell is already running, don't see anything. Okay. Oh, here it is. Okay. For getting all the different Miller indices, we were at the Kikuchi lines before we got so rudely interrupted by this thunderstorm, I guess. Didn't happen before. So we were talking about these diffraction patterns and how it is related to Bragg reflections. Obviously, there is a Bragg reflection. I should stop my video. Obviously, there is a Bragg reflection going on in here, so we should be able to just do that with Bragg reflection. How are we with our installation here? So we're still good. Still good here. Okay. So we define a crystal again as we did before. Don't need to wait for plotting the atoms. That shouldn't have taken that long. Something. Guys, not sure as we have. Can you still hear me? Yeah, I think so. Not gone
Yep,
off.
everything's fine.
Okay, something got. I think the problem is that I didn't restart my runtime here. And so Google gets confused with it. So I restart my runtime. Should be working for you guys. So if you just go down. We do our convergence angle, and then we calculate everything with this kinematic scattering, and all we need, of course, is the atoms, but into the atoms, I put a dictionary where I put the acceleration voltage, convergence angle, and of course, very important, my excitation error. So we then plot that, at least my version right now has no problem with that, because that should go done in seconds. It's not working. Okay, I think I confused that. Disconnect and delete runtime. Should have done that to begin with. So let's do that again. Load it. Yeah. We have to reinstall everything. But while we are moving down here, we can talk about, okay, we don't have the pictures now. Because, say, again, purely, this is purely trigonometry again. Everybody having a break here, I guess. So we wait for that. Then I can show you what I mean. The Kikuchi lines are the bisection of where are we here? Okay, still working on it. The bisection between, say, this is our 0 point, here would be our break point, and the Kikuchi line is just a bisection between them. Because our Evald sphere is so large, we don't really see the curvature of these cones here, right? And so the distance from our break peak to our 0 point is the same distance as between the two different Kikuchi lines, our excess and deficient line. So how are we here with our structure? Okay, see whether we can now do the visualize them down. We put our experimental conditions and we calculate everything. Takes no time at all. And then we get our diffraction pattern, very simple one. And now we do the Kikuchi lines. So all we do is we make a bisect between one of these points here, right? And that is our Kikuchi line. We do that for all of these different ones. And this is now our Kikuchi pattern. See? Between those, that is the bisect of all of them. And the key thing is that the symmetry of the Kikuchi lines is the same symmetry as we have here for our break peaks. So it's 2 mm in that case, so it's rectangular, or in this case, a parallelogram. So if we plot the whole thing of a diffraction pattern, then you can see quite a ways. This is what we will get in our zero beam, zero disk. And if we plot that for the whole library, we get from the Kikuchi lines some amount of information already, or the same information on the symmetry as we have from the whole Kikuchi pattern. If the symmetry is very high, you have a lot of Kikuchi lines, and that is how you go to recognize on the microscope where the zone axis is. So if it's a lower order zone axis, you have a lot of these Kikuchi lines coming together. The wider the Kikuchi line is, or the Kikuchi band, I should say, the smaller the distance in real space. So a small order zone axis will have very, very thin Kikuchi bands. And so that's another idea of what's going on. The opportunity for machine learning is obviously you're anywhere in this Kikuchi pattern, and you know exactly where you are, and then you say to the microscope, hey, I want to go to the 100 zone axis of this material, and the microscope says back, or the machine learning algorithm says back, no, you can go there. That is not enough for the tilting. You can go to the 110 instead, blah, blah, blah. So something like that would be good. And the training things are all here. If you tilt out, and here we have some amount of tilt, so we just put the mistilt in the alpha direction, in the beta direction, then you get a so-called Laue ring in your diffraction pattern, but even though your zero beam is now over here, the center of your diffraction pattern, or the center of your zone axis is still recognizable, and all you have to do in the microscope, get this part in coincidence with your incoming beam. So that's what you need to be doing, and you use the Kikuchi map as a map on a road, and you follow the thin ones to the next lower order zone axis. Now comes the important part. How can we go and assert that this what is the excitation error. And again, it's purely trigonometry. All you have to do is go and get triangles with a right angle. And we put an excitation error here, and we can see where our excitation error puts the Kikuchi lines. Okay, let's go to perfect condition. So 0 excitation error. And we see the Bragg peaks coincide with the Kikuchi lines and the zero beam. So our Kikuchi lines, one Kikuchi line coincides with the zero beam, and the other one with the Bragg condition, because this is the distance. If you go negative, a little bit larger, just sure whether that is too large or not, then you can see how that changes out. So if you want to be in perfect Bragg condition, all you have to do is look at the Kikuchi lines, and that's how we usually align that as well. Okay, so the key thing is that the Kikuchi lines will give you an idea of where is what excitation error, and then you can use that creatively in your experiments. Okay, how much time did we lose? In 20 minutes. Okay, let's go to the next book. Now we do the same thing with the higher order Laue zones. Oh, that's not the one I wanted. I want to have the whole lines and how they are related to what's going on. We open it in Colab. We run this instance. And again, we need, for doing that, everything is stored. We need the PyTemlib from Picroscopy. Cipher readers. Okay. So if we go for the same kind of thing as we go here, we have a scattering to very high angles by the higher order Laue zone. So we have an excess line in this higher order Laue zone ring throughout in the angles, but we have a deficient line. This deficient line is now not longer related to a very short Bragg peak, but to a really, really, really huge one. And it will show up in our zero disk. That's what we want to see. And that is super precise if you want to determine any kind of lattice parameter, especially if you want to determine any kind of strain. And as we said, we can do that locally. We use silicon again, just for the fun of it. We're using our 100 kV. We use the 2-to-1 direction here. And we use an excitation error in very large maximum milli-indices. We want to go out to the higher or the Laue zones. They have higher milli-indices by definition. Okay. And this is how the diffraction pattern looks like. It's a mess. Okay. Let's look how we do our Holtzline construction. Again, we have an incoming beam. We have an excitation error, and we do the same thing as before. So if we have it perfectly aligned, perfect Bragg condition. So we have the incoming down here and over here, and we tilt it out a little bit. Now we have an excitation error, and we have our third dimension vector in reciprocal space here, and we get a deficient line over here. We can do the trigonometry again, best done at home and check it out, but there's nothing really hard about that. And that means it's purely trigonometry, and so it can be done extremely fast, and you can get this training data extremely fast. So we get a rotation matrix to go down straight, and we determine the nearest zone axis. We calculate the interatomic distances. And now we have the Kikuchi lines for this higher order zone axis. And you can see there are a lot of them going on. The red ones are the Kikuchi lines, they're a bit outside. The blue ones are our completely equivalent one, deficient lines from the higher order Laue zones. So any small changes in, okay, I shouldn't, Google doesn't like that. In your own computer, it will actually highlight what is the Miller index of the different lines here. So I can't do that in Google. It doesn't like the event manager I'm using here. So let's do the same thing with graphite, a little bit more interesting. And I go in the third dimension with my higher order Laue zones. And I see I have relatively complicated pattern here. And you can use to simulate that, of course, for different acceleration voltages. I want you to, okay, I shouldn't have done that. Maybe I start it again. I'm not going there. Okay, I wanted to start it anyway. What we want to do is we want to look at that. How do I? You know? Okay. Maybe if I do this, then it doesn't activate it. I want to look at the blue kind of circle or polygon that we have in the center of our Holz lines here. So let's reduce that. So it was 61.49. That's the full diffraction pattern. And then it calculates, you see that the inner, this polygon in the middle gets smaller. And if you play around with it at 60.49, all of this Holz line collapse in a single point. So it means, and let's see how accurate we can do that. So we zoom in here a bit. Okay, I did a really good job when I did that the first time. Okay, so we are now at 0.0025. Let's change my acceleration voltage by 10. And you will see that this is already changing your Kikuchi pattern. So a change of 10 volts in the acceleration voltage will already give you a different pattern, and you can monitor that. So this is totally, with the right condition, observable. 100 eV is also possible. So if we do that, we can calibrate with a known sample very accurately where we are with our electron microscope. If we then go and to an unknown sample, we know exactly our experimental conditions. If you think that if you put in 200 kV, you will have 200 kV, that is not going to be the correct thing. Some electron microscopes change the voltage up to 3000 volts, backwards and forwards, 3000 volts. Okay, completely different from our 60 volts. And the reason they change that is usually downwards, right? 57 is to have for energy filtered imaging or diffraction, so that they have some amount of flexibility with the acceleration voltage and can increase that as they want to for different and have different energies on the optic axis and on the within the alignment of the microscope. So you have to be careful. Also, there are small deviations, obviously, at high voltages. It's not completely trivial to measure them. So let's go back to the Kikuchi lines, because on the bottom here, now that we know how powerful that is, we can look at that. There's my. Can look here at the appendix, and we can see what we are doing here. So if we have a line, we can do that by defining a start and end point, or 2 points where they go through. We can do that as we do it in mathematics mostly. We have the intersection with the y and the slope. So that's usually how you fit a line. But you can also do it with, if you go up here, you see that you can do it with making a bisection here and go for this smallest distance of the line to the origin and to the angle it does. Now, if that reminds you of something, that's exactly what I want you to do, is because if we have this Bragg peak here, in polar coordinates, then we have the distance from the origin to the Bragg peak, and half of that is where we have our Kikuchi line. And if we have this Bragg from the distance, if we have the angle, the 9 degrees to it, that is where we have our Kikuchi line. And since the construction is the same thing, even though a bit screwed out to higher angles for the Holtz lines, if you do just the Bragg calculation, you automatically, if you put the Bragg spots in polar coordinates, you get your half space, your lines in half space. Let's go back down here. And so without any kind of extra mathematics, we know exactly where they are. So polar coordinates and half space are your friends. And if we just plot our Kikuchi lines, we are done already. We don't need to do anything extra. So there is no difference between kinematic diffraction, Waltz lines, and diffraction lines. So whatever I did is I just plotted it differently. And the idea is, of course, you can now easily add any kind of rotation in plane because it's just a polar coordinate and you can move things around. And so you can fit any kind of diffraction pattern extremely fast, or you can generate them. In experimental image, you have, okay, let's get rid of this one, maybe, okay. Your Huff transformation will get you the same information. So for all possible lines, you get a bright spot in your Huff transform, and this Huff transform, like here. So what you do is for each spot that you have in your pattern, you say, okay, if it is a line, it has set distance and would have all angles. And if you have this a few times, then so all different, so you have one spot and you have all different lines. So you calculate what that would be in Huff space. And a line, of course, then is where they all meet. So any maximum in Huff after the Huff transformation will be a line. Now, don't try to do anything now. You have it already in the perfect description, right? So you can directly compare the Huff space with the simulation by just going into polar coordinates and half your distance from the center. And that is true for both the Kikuchi lines and the Waltz lines. So the Huff space is your friend here. Okay, I did it again. And you can compare that directly with your experimental images. So nothing really has to be done very strenuously here. Or mathematically involved. So huge amounts of data can be generated in no time. How accurate is that? And so just for you to play around with that, I have one notebook here that we open in Colab. That is the one with the example. And here we want to look at how accurate can we be? And how accurate can we compare that to a diffraction pattern? And that means how accurate can we determine the strain? And now we are not only after the in-plane strain as we were with the images. Now we are going for the full shear tensor of the material. And while we are waiting for that, this is not the latest version. Because, yeah. So here we have missed my overview part. Okay, so we wait here for another second or so. So this is going to be the diffraction patterns that we want to analyze. How accurately can we do that? What is the accuracy of our strain tensor? That's the smallest one, okay. So it is a silicon sample and it is from a book, Nanodiffraction of Spence and Sewell. And we want to just look how good we can do that. And So we download this image. As I said, it's just copied out and we plot it. I use experimental conditions, say use in the book. There was no mistilt. It's a 2-to-1 zone axis. I selected maximum excitation error and a maximum Miller indices. So that's, again, as we did before, we just look at all the different Miller indices, see whether they are allowed, and have the excitation error within the distance. And then we are getting our polar coordinates, make half lines out of that, and then we overlay that over the figure. And for all practical purposes, you would say, okay, super, excellent agreement, blah, 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 everything is perfect. This is, however, not the accuracy that you can achieve on this kind of diffraction patterns. We see that these ones are off, so this line here is off, this line is off. Generally speaking, what people do to align that in the past is just looking at these crossings here. And these crossings are perfect. And however, the higher ones out here are not. And you can see how they are deviating a little bit, and over here as well. So the higher angles are not perfectly done. So let's see what the problem is and whether we can fix it. Before I forget it, I want to alert you to the dynamic effects that we have here. And that is that, sure, I can do that nicely here. We have this in that line, and effectively, that's not what these lines are doing. These lines are actually split, and you have some dynamic effects with that. So this can happen, and these kind of dynamic effects are not avoidable. And so since we know about it now, we ignore that part. So let's see how more accurate we can do that. I first of all look at how round my disk is, and this disk is a little bit off. You can see there is a little bit of a deviation of perfect roundness, and that will be the objective stigmation. I can add that because it's a simple distortion at this point in time. And then my higher orders already look better. Okay, so we have changed the distortions, and suddenly everything is perfectly in here. I also used a mistilt. So let's get rid of the mistilt, and the mistilt is extremely small. So we are talking about 0.03 milliradians, that would be 30 microradians, without the mistilt that I introduced. We have very small deviations here, here, and here. So we're already very, very close, but you can make it perfect. And if you add that to it, if you zoom in a little bit, you will see that that is actually necessary. Also, if you look at these parts here and these crossings, you will see deviations from that. Okay, so these are the main ones. So we went only up to the Miller indices up to 9, but you can see there are a few more in here. This one is overexposed. So it's due to the print and everything. So obviously the dynamic in the diffraction pattern is very high, and it's very hard to reproduce that. So let's look at that and see whether we find them. Okay, here we go. Got a lot of them. So what did we do? We just increased the maximum HKL, but we left excitation errors the same. Okay. So we have a lot more of them. And if we zoom in here, we see that these weaker ones are also within here. They're a little bit off, and you can play a little bit with the mistilt, and you could actually probably reduce even that kind of agreement. But look at this kind of triangle of the weak ones. So the agreement is now astoundingly good. And the question is, what is it quantitatively, right? So let's look at a unit cell. And in the input, we now add some amount of distortions. The distortion in microscopy is defined on the unit cell. So if we have a tetragonal distortion in the X or in the C direction, so that is perpendicular, both of them will be visible. And this one in the non-diagonal elements, there would be a shear. Now we can play around with that and see how small of a change can we see. The unit cells are given, as always in the atomic simulation environment, in angstrom. So here's our perfect match, right, with the small changes. So let's go and add 5 picometer. Okay, it's angstrom, so 5 picometer. Complete disaster. So 5 picometer is way too much for that. Okay, let's get with an accuracy of half a picometer. Clear changes. We see how that is moving around 0.1 picometer. Still visible. Okay, so we have very small deviations here. So we had in the order of 1 picometer in the image for the plane strain to be determined. Here we have now the accuracy of tenths of a picometer, and we have it here in the planar strain. Let's see in the third dimension. Deviation up here, deviation here. So clearly we see a deviation. Let's go with a half a picometer. Let's be crazy. and we see that we have really huge deformations here. If we look at this angle, it changed. So there's a new one. So, okay. So we have a shift in the angle here, of the crossover here. We have a shift here. All of that shifted up. And down here we have large deviation. So generally it just doesn't fit anymore. If you have a good reference for that, you know exactly how accurate you were, and then this is what you can do with scanning seabed pattern or 4D stem, whatever you want to call it. Let's go and put some shear into that. Again, we go to the perfect conditions. Half a picometer. And shear like say tetragonal distortions in the Z direction, in the X direction, will get us to strong deviations. And so you can now access with these kind of matching, which we did here by eye, which of course is silly. It should have been done by in half space. That's what we normally would do. And finding this kind of patterns and the right experimental conditions and so on can be, of course, be done quickly with machine learning algorithms and doesn't have to go through just a simple grid search. So there's lots of opportunity here. And the reason for that is this is a diffraction method that is super accurate with a lot of information. And so you can determine strain, you can determine strain field around the precipitate, you can determine strain field around the dislocation with and without segregation to it, and so on. So it's one of these techniques that is super precise and, as you see, relies only on kinematic diffraction and therefore only on trigonometry, which in the matrix implementation of trigonometry in NumPy is directly available to you through PyTemlab. So the key thing for acquiring this kind of pattern is, however, that you use energy filtered diffraction. That is a Gatan image filter or an inline filter in microscopes available. Otherwise, you're restricted to very small thickness in a material where they show up really very accurately. Okay, I didn't see anything in the chat, so that's it from me from diffraction. If we have any questions here. Okay, everybody is completely overwhelmed by trigonometry. That happens easily. So anyway, think of these kind of informations. Okay, do I hear somebody? No? Okay. Think about this information you have in your diffraction pattern and the opportunities that nothing is simple in machine learning. Yeah? Relative simple. I think you don't know how long you can spend on matching these kind of patterns. Of course, nothing is simple, but relative simple and doable, and helping you to get super quantitative data out of this kind of diffraction pattern. That's what I should have said, right? Useful. And yeah, if you know what you're doing, then you do your simulation beforehand so that you know how much information you will have in there. So, okay. Well, if we have no other questions, then I thank you for your attention. And you'll see me again in 1 week when we do image simulation. In between, we will do some more machine learning on Tuesday. And after I have done the image simulation, we will do the 4D STEM analysis. But there we restrict ourselves for the coherent case. So we have to go through that. The coherent case will be using the thermal diffuse scattering. So we have to look at the dynamic scattering of thermal diffuse data. And we can do that most efficiently if we do that in the image simulations that we have to do for sequence imaging anyway. So basically, we determine what the STEM data look like, and then cut out, as we do with our detectors, the information that we're going to use for the imaging or have used for the imaging to match it. Okay, so everybody have a good weekend then, and hope to see you all in a week. And one important point. The 4th of July is on Tuesday, so we shifted the lecture by 1 day, so it will be on the 5th instead of on the 4th for the machine learning part of some more machine learning parts on. Okay, and I'm out blinking. I think it's on imaging, but it's a more involved machine learning. As we go along with this lecture series, the machine learning part will go more efficient and complicated and useful. All in that order. Okay, thank you. Bye-bye.